Breathing. It's probably the most important thing we do, right? But most of the time we don't even think about it. It's just on. A perfect, unconscious autopilot system. But what exactly is that autopilot system controlling? And more importantly, what happens when it fails? So let's dive in and take a look at this incredible biological machine, see what makes it tick, and what happens when things go wrong. Okay, but before we go any further, let me ask you a question. Think about that powerful, primal urge to take a breath. What do you think your body is really demanding? Is it screaming for more oxygen, the gas we all know we need to live? Or is it reacting to the buildup of carbon dioxide, the waste gas we're always trying to get rid of? If you said oxygen, don't worry, that's what most people think. But the real master regulator, the gas that's pulling all the strings, is actually carbon dioxide. Our drive to breathe is overwhelmingly dictated by the level of CO2 in our blood. And honestly, understanding why that is the key to everything from exercise physiology to how you'll manage a patient in the ICU.
So here's our game plan. First, we'll look at the system's overall mission. Then we'll check out its sensors and its command center. After that, we'll see it all in action, and then, and this is crucial, we'll look at what happens when this whole system goes wrong. All right, first up, the mission. Before we get into all the nuts and bolts, what is this whole system even trying to do? Well, at its very core, it's all about keeping that perfect internal balance, what we call homeostasis. And just think about the incredible balancing act that's going on here. On one hand, the system has to be super precise, keeping our arterial CO2, O2, and pH within these tiny, razor-thin margins. But at the same time, it has to be unbelievably flexible. It has to just hand over the controls when we want to do something voluntary, like talk or sing, but then reliably take command the second we fall asleep. It's amazing.
Okay, so to control something that delicate, you first need good data. And that brings us to our second section, the body's super sophisticated network of chemical sensors. These are called chemoreceptors, and they are constantly tasting the blood to see what's going on.
Now, what's so cool here is how the work is divided up. We've basically got two teams. The peripheral team hanging out in our major arteries. They're the fast first responders. But the central team, located right there in the brainstem, they're the true heavy hitters. And you can see it right here on the chart. They are the dominant drivers, responsible for a whopping 2/3 of our entire response to changes in CO2. These peripheral guys are posted up in some prime real estate. You've got the carotid bodies right where the main carotid artery splits, and the aortic bodies sitting right on the aortic arch. This allows them to constantly sample the blood fresh from the heart and send these lightning-fast updates straight to the brain.
So how do the big players, the central sensors, actually work? Well, it's this brilliant, indirect trick. See, CO2 is like a ghost. It just slips right across the blood-brain barrier, no problem. But hydrogen ions, they can't get through. So once CO2 is inside the cerebral spinal fluid, an enzyme jumps on it, turns it into carbonic acid, and that releases hydrogen ions. And that's what the central sensors actually detect, the change in acidity, the drop in pH. It's not sensing CO2 directly at all.
Okay, so we have all this amazing sensor data streaming in from all over the body. Now, it all has to be processed. And for that, we go to Section 3, the command and control center for all of respiration, the brainstem. Tucked away in the pons and medulla, this is where all that incoming information gets put together. And while there are a bunch of different parts involved, if you're going to remember one name, make it the pre-Boettinger complex. Think of this as our core pacemaker. It's the central rhythm generator that creates that basic fundamental drive to breathe in.
And if you want to know just how sensitive this whole system is, look at this number. For every tiny 1 millimeter of mercury increase in your CO2 levels, your ventilation goes up by 2 to 4 liters per minute. That is an absolutely massive response to a minuscule change, which just goes to show you how seriously the body takes keeping CO2 in check.
So we have the sensors gathering data and the control center making decisions. Now for the final piece of the puzzle, the output. How do those signals from the brainstem actually turn into the physical act of breathing? Let's follow that signal from the command center right down to the muscle contraction.
The output is actually pretty straightforward. That signal from the brainstem travels down motor pathways in the spinal cord and goes straight to the real workhorses of breathing, the diaphragm and the intercostal muscles. The brainstem's commands tell these muscles exactly how hard and how often to contract, which is what controls the rate and depth of every single breath we take. And like any really well-designed system, this one has built-in safety features. A perfect example is something called the Herring-Brier reflex. As your lungs fill up with air, stretch receptors in your airways start firing. They send a signal back to the brainstem that basically says, okay, that's enough, and it acts like a brake, stopping the inspiration to make sure you don't overinflate your lungs.
And this, right here, is where understanding all this elegant physiology becomes a literal matter of life and death. For anyone going into clinical medicine, knowing how this system can break down is absolutely critically important.
A tragic and way too common example is opioid-induced respiratory depression. Opioids are incredible painkillers, but they come with this really dangerous side effect. They directly hit the mute button on the very neurons in the brainstem that are responsible for generating our drive to breathe.
Here's the fatal cascade. The opioids go into the brainstem and they shut down the pre-Bitzinger complex. The signal to breathe gets weaker and it gets all irregular. And eventually that drive to breathe is completely snuffed out. Ventilation just stops. This is how people die from an overdose.
But let's switch gears from system failure to a really powerful example of its adaptability: exercise. Because here, the exact same principles we've been talking about are just scaled up to meet these incredible new metabolic demands.
Look at this timeline. It shows this beautifully coordinated response. In phase 1, the instant you start to move, your breathing just jumps up. That's probably an anticipatory signal from your brain. Then in phase 2, the system settles into this high, steady gear, with all those chemoreceptors fine-tuning everything to perfectly match your CO2 production. And finally, in phase 3, as you cool down, your breathing gradually returns back to normal.
So we really end right where we started. Whether you're at rest, fast asleep, or in the middle of a workout, that fundamental principle is always true. The single most important thing that drives your need to breathe isn't the oxygen you're trying to get, it's the carbon dioxide you desperately need to get rid of.
And that leaves us with a really fascinating question to think about. We've just spent all this time establishing that CO2 is the undisputed champ, the master regulator. But what happens when you go to high altitude? All of a sudden, low oxygen is the big problem. So does CO2 still get to call all the shots? How does the body's autopilot system recalibrate when the entire game has changed?